We're about to embark on a part of physics that requires us to analyze things not in just one dimension, but in two dimensions. Typically, those dimensions are in the x direction, the y direction. Sometimes we'll use cardinal directions such as east, north, south, and west. But regardless, we could have things moving in, the northeast direction. Well, then we are traveling in a direction not along one of our two major axes. So we need to be able to represent that in all cases, whether you're actually moving in one direction or in a combination of directions on the coordinate plane. In order to do that, there's a concept called vectors. And we've already worked with them, but we just didn't call them vectors. A vector is a measurement that has magnitude, and magnitude just means it has a quantitative value. We are able to measure it with a scale, and direction. And so we did displacement, where we knew something would move, 5 meters to the left, or the object dropped, 2 meters downward. That they are vectors because it has those measurements have a magnitude, a value, and then a direction. Same thing with velocity. Also, same thing with acceleration. We needed to know if things were accelerating in a positive way or in a negative way, and that positive and negative did represent direction. There are other things that are vectors. What we're going to get into soon enough is, of course, force. Which way are we pushing something, and how much are we pushing something? And then there are things that are not vectors. And they're called scalars. Mass, kilograms. There's no physical direction to mass. It's just 10 kilograms. It's not 10 kilograms south. A heat, in joules, or energy, I should say. Any form of energy, really, it doesn't have direction. And time does not have direction. I know people will say, well, time is always moving forward, but it does not have a physical direction. And of course, some people would argue that, well, we can travel in either direction in time. Or some people would argue that time doesn't even exist at all. That's a whole can of worms for another day. So, let's take something simple like a displacement, moving somewhere in a direction. Well, in order to represent that, if say you went 5 meters to the east, or 5 meters to the positive x direction. And by the way, we will be using north, south, east, and west quite a bit. And that's just going to match our regular coordinate plane. So if I say something's going to the east, typically we say it's positive. If I say something's going to the west, typically we say it's negative. North and south, accordingly. So let's say we're going 5 meters to the east. And I'm going to represent that as vector A. Typically, vectors are represented as a letter. It doesn't have to be capital. And typically, we put a little line over the letter. Some books will use this little half arrow. Some books will use a full arrow. Some books just put a line. Some books just bold the letter and don't put an arrow to represent a vector. But on this board, for me, it's very difficult to bold something. So I will typically write a little half arrow above it, indicating that it is a vector. And that's important to know. And so we have this vector to the east. Now, to represent this vector, we draw an arrow, and you draw it accordingly. You can label it vector A. And once it's labeled vector A, and if we have a notation nearby, we know this is worth 5 meters because of its scaling, or you could label it directly. And you don't have to put the direction because the arrow indicates the direction, assuming some kind of indicator or key or legend is nearby. The parts of a vector, and vectors do have anatomy. There is a tail to the vector. There is a head to the vector, an arrowhead. Now, if we are to represent another vector, and let's say we are going to do vector B. And I mean, you can call it doesn't have to be A and B, it could be vector S, it could be vector T, it could be vector, whatever letter you want to use. Obviously V and X are common because of velocity and displacement in our class. But if you do this and you talk about another vector in the same conversation, in the same problem or the same page, well, when you draw that arrow, it had better be, to scale. Now, I don't have a ruler in front of me, which I do. I guess I should have measured it beforehand. But if this were, 20 centimeters, then this had better be 40 centimeters, and it is, amazingly, about 40 centimeters. The scale's 2 to 1, 1 to 2, because the vectors must be proportional. As a matter of fact, you can, on your paper, represent these vectors with a ruler, and we'll get into it soon enough, with a protractor, to give them the appropriate direction and scaling. And that's important. Obviously, these vectors could be to the north, they point upward, or to the south, they point downward. But also vectors can point at an angle, not along one of our major axes. In order to represent that, I'll keep vector A here. Let's take vector C and say it's 5 meters, 30 degrees north of east. Now, 30 degrees north of east. What does that mean, and how do we do it? Well, this really means you are 30 degrees north of the east axis. And so you have to think about your axis here. And if you're 30 degrees north of the east axis, well, here's my east axis. That's your reference. You're going to go 30 degrees north of it, so you're going to kind of sweep upward. So if I kind of put an imaginary coordinate system here, coordinate plane, so what we're going to do on this little coordinate plane, we're going to go 30 degrees north of the east axis. So we're going to kind of sweep upward 30 degrees north from the east axis. And we'll draw our arrow. We have to use our appropriate scaling, so hopefully it's about the same length. I can probably call it right here. And I'm going to call this vector C. Now, sometimes we don't use north of east, or sometimes you can do south of west. You can do a bunch of different variations of it, but the second indicator is typically your reference axis, and the first indicator is which direction you sweep from that axis. This could also be represented as this 5 meters at 30 degrees, and if it just says 5 meters at 30 degrees without any north, south, east, or west, without cardinal directions, it's just a Cartesian coordinate plane. So you would just do 30 degrees as you would in math class, because in math class you always start at 0 degrees at the x, and you would always read your degrees around in this way. Now that means you could get something as strange as, and we'll do it, you could get vector D. Another problem, let's pretend that we are switching gears, we're no longer on a coordinate system. If you get vector D is 75 meters at 210 degrees. You could get that, and that's just like math class. You would draw a coordinate plane, you have x and y. You know that this is your positive x. You would go around your 210 degrees, and then you would draw your axis. And you would need some kind of scaling off to the side to say, like, every centimeter is 10 meters, or some kind of scale to represent that arrow, that displacement, that vector. So we have other things to discuss, how we manipulate vectors and how we analyze vectors, and that's all to come. So stay tuned.